Yeah, so like Chris said, like for a number of years now, I've been working on programming languages for interactive computation, and the the scientific question here is that when we think about computers, like if you go and you look at a textbook on like Turing machines or hardware architecture or something like this, there's a lot of um, there's a lot of focus on this stuff that's inside this box. So like the CPU, the hard disk, so like memory, reading, writing functions, that sort of stuff. And there's a whole lot less like um, research attention by like sort of the theoretical community broadly construed on like all this other stuff, that the means by which we actually interact with a computer. So like our computer is doing its thing, but somehow it's got to send answers back to us, and we have to give it instructions. And one of the things I've been interested in for a long time is like, how do you model that mathematically, and what sorts of languages and program models come out of thinking about interaction. And so what I want to do is first start by just talking a little bit about models of computation. So when we talk about a computer, you can ask the question, well, what is a computer? And on the one hand, you're going to have one idea which looks like this. You've got a piece of silicon, like a piece of rock with some scratches in it. And when you electrify it in just the right ways, you can read out other electrical patterns from it, which you can interpret as doing arithmetic. So, in one sense, a computer is this like really concrete physical object. But I tend not to look at computers that way. So the way I tend to look at computers is something more like this. So if you wanted the full experience, this would all need to be in computer modern. But I tend to think of computers and computer programs in terms of this formal mathematical approach, lambda calculus type theory, things like this. And the interesting thing here is that each one is in some sense an abstraction of the other. So we have these pieces of hardware that like extremely clever engineers have designed, and we need to control them. So we invent programming languages in order to get them to do things, and the things that we get them to do are like the languages, the programs we build, like sort of arise from the capabilities of the underlying hardware. And then in the next generation, hardware architects come and look at what people are doing with the computers, and then they adjust their models of computation a bit more. One of my favorite examples of this, of like just how incestuous the cycle can get, is that in the latest revision of the ARM hardware specification, the ARM architects added assembly language instructions for the specific purpose of making JavaScript run faster. So it turns out that when JavaScript does arithmetic, it doesn't do it the way that like C or Java or Smalltalk would do it. It puts all its numbers into floating points and then pretends they're integers. And so that's why JavaScript integers are 53-bit integers. So it's a kind of unusual programming model. And in order to make the way that JavaScript represents numbers run faster, ARM has added some features. So there's this dialectic or mutual coevolution between the physical hardware that we build and the programming models that we build on top of it. And the thing is, though, that like when you build one of these formal models of computation, like you have to have a idea of what kinds of programs you're modeling before you build your formalization of it. And for a really long time now, if you go look in a computability textbook or something and read about Turing machines, what it'll say is something like, okay, you have a program, and you have a Turing machine, and on the tape you write some bits, and then the Turing machine will grind away for a while, and then it'll end in some accepting state, and you read the tape, and that's the output. So the formal model of what a computation is a model of something, a function, something that takes some input and produces some output. And so in some sense, it's really all about the inside of the box. Did I get a question? No, I guess Gather just made a sound for some reason.
No, sorry, that was just me telling people how to do questions. Please continue.
Okay. Yeah. So if anyone wants to ask questions, feel free to ask me anything. I don't mind interruptions, and for RSI related reasons, I have to handwrite all my slides. And so if anything is like illegible or partly legible, please feel free to pipe up, and I'll be happy to clarify. Okay. So our fundamental abstractions of computers, our formal models of computers, are things that take inputs and produce outputs. And in reality, though, this has been a bad model of computers for a very, very long time. And the reason is that we think about a real interaction with a computer as an interactive process. So you give the computer a command, it gives you a response, and then you scratch your chin for a minute, or maybe not if it's a video game, you don't have time for that. And then you give the computer a new input. And so there's this cyclic process of feedback where inputs beget outputs, and outputs lead to the computer getting new outputs. And so there's like this cycle between input and output. And so the formal model here is like sort of inadequate to properly model the way that we actually use a computer. And this means that when you're doing math about a computer, you're going to struggle a bit to capture the concerns that naturally come up when you're building interactive systems. So in some sense, this talk is an advertisement for the idea that when you're building a mathematical model, you can't take there's always this temptation to say, okay, well, the mathematics is like beautiful and clean and comprehensible. And that frees me from having to think about what kind of crazy thing like ARM and GCC are doing this week. But there really is a lot of value to thinking about these things in like sort of more, almost more scientific terms, where the model, where the thing that happens in the real world is the data that you use to produce your model. So there's like some feedback between the way you use a computer and the way you think about using a computer. In fact, I even said a moment ago, our formal models of computation are inadequate, but it's not so bad. For a long time, it wasn't so bad. And what I'm going to do is I'm going to go back in time to the early 1970s. And I'm going to show you, I think this is called a TTY33 ASR console. And this is a teletype. And this was the first machine that let people interact with computers. So prior to the invention of the teletype, the way that you interacted with a computer, like ENIAC or something, is you rewired the computer to give it its input, and then you ran it for a while, hoping that no vacuum tubes would blow up while it's running. And then at the end, you would go and look at all the voltages and write them down on a piece of paper, and then figure out what the output of the computer had actually been. And so teletypes were actually, in their time, revolutionary. And so what they consisted of was two things. On the one hand, there's a printer. And so that's that little green thing I've circled up there. And on the other hand, a typewriter. I almost said a keyboard, but it's actually a typewriter. And they originally took typewriters, and then when you hit the hammer, in addition to printing something on that printing paper there, it would also close a circuit and send a message to the computer, which is the thing in the background behind this teletype console. But sort of appropriately for the talk, the computer is in the background and the I/O device is in the front. So So these teletype consoles were how people could interact with computers. And even today, when you open up like Mac OS or Linux or something, you call a terminal window a TTY, and that stands for teletype. And so you type in something like ls, and it'll give you a list of files, like maybe talk.tech and talk.pdf, and then you can give it a command like rm and delete something, and then when you give it another command, and it can list your files. And back in the 1970s, this little script right here would be exactly what's printed out on the printer paper. So as you interacted with the computer, reams and reams of computer paper would be used. And in some sense, this is why Unix tools are so terse in their output. It's because if you're literally printing in order to display any output at all, it's sort of you're literally like spending money to have any interaction with the computer. But one thing I want to highlight here is that the old model of computers, input to output, isn't a terrible match here. So you have an input, like this purple thing, and then it gives you an output, and then you can give the computer some more input, some more input, and then get out some more output. So if you think of just one interaction with the computer, like you type one command and then you get one output, then the model, the input-output model isn't so terrible. But if you're thinking about and so what happened next, okay, I'm about to say what happened next, but this is not actually what happened next. This is more a reconstruction of how the development of ideas could have happened rather than how it actually did happen. But this idea that maybe the atomic unit of interaction is one input and one output, that actually has like a lot of value. And so here's another computer with its teletype. And so the idea here is that, if you don't have that teletype machine, the stuff in the computer is totally opaque to you. There's no way, short of showing up with a voltmeter, of figuring out what your computer thinks its view of the world is. The only way you can communicate with the computer is via input-output. And so you can imagine in the limit, like every single keystroke gives you one very simple input, and every single byte that the computer writes out is like one very simple output. And so this leads to the kind of the simplest model of interaction that people have thought up. And this idea is, we said, the computer is opaque to us. And so what we're going to do when we're building a formal model is we're going to say, I'm going to have a set Q, which is going to be the set of possible states that the computer could take on. And the computer is currently in some state. And the way that I'm going to model interaction with the computer is by giving a function, a transition function. So you say, what the transition function does is it says, if you give me an input and the current state, then I'll give you an output character and the output state. And so, if you've looked at like automata for regular expressions or things, it's actually super similar to this. So if Q is a finite state, then this little setup here, where you have a finite set of states, a current state, and a transition function, that's what are called like finite state transducers or Mealy machines or things like this. And if you want to model fancier forms of interaction, you can let Q be an infinite set. So all the possible states the computer can take on. And so now here you can sort of see the shadow of the original input to output model, where we still are getting inputs as the input to delta, and we're still getting outputs, but now we have like this state that we can use to see how the input is transforming the current state, the current state of the computer. So every time you give the computer a command, it'll match that against its current state, and it's going to produce an output along with an updated state. And so this model of... Hello, did I get a question? No. Okay.
Yes, there is actually a question. Do you want me to read it, or do you want to check the chat?
I'll just check the chat here. So the question, yeah, so Yuri Raijine, I hope I'm saying your name right, asks, is the expression of the current state not also a form of output? Okay, that's a great question. And to understand the answer to that question, you have to look at this picture, because we're building a formal model and we're abstracting a situation in the real world. So the computer here, I wish I could do this presentation on my tablet, because then I could draw on this presentation. But the computer, if someone hands you a computer that doesn't have any I/O devices, in fact, let me show you one as a matter of fact. So if you look at my screen, I will show you my phone. This phone is actually broken, and the display doesn't work. And I think that the phone still works, but the display doesn't do anything. Like periodically, I hear it beep at me. But other than that, its internal state is totally hidden. This computer right here has a state queue, but I don't know what it is. So we can't think of the state of this computer as something we can easily observe. Like the things that we can observe are the inputs and the outputs. The actual memory state of the computer is something that's hidden from us. And this is actually like really useful if you're, say, writing a compiler or something, because the fact that the user can't see the intermediate states is what licenses you to do all kinds of crazy compiler optimizations. Okay, was that another question? Okay, thank you. Yeah, so the point is that the state of the computer is in some sense hidden from us, and we interact with the computer by giving it inputs and reading out the outputs. And then, if you iterate this process of giving inputs and taking outputs, you're going to give it like sort of a stream of inputs and read out a stream of outputs. And all along the state of the computer will evolve in like some fashion that we hope is beneficial. Okay. So this model of computation, I said was either the first or nearly the first model of interactive programming. And I mentioned before that this has a certain resemblance to the finite state automata that you use to implement like regular expressions and lexers and things like this. And in fact, it's not just a resemblance, it actually all works perfectly that way. And in the 1980s, there were a number of languages called the synchronous programming languages that really pushed on this analogy. Like the idea behind these programming languages was that if you have like some high reliability situation, like in airplane avionics or train controllers or something like that, you are in a situation where you need a user interface, but you also need for that interface to never crash. Because if a jet plane's control computer like goes on the fritz, then this is really bad for hundreds of people. And so in France, like a number of programming languages called synchronous programming languages were invented. So two of the most famous ones were Esterel and Luster. And what both of these languages do is they give you a DSL, basically a DSL for specifying a finite state automaton, which accepts inputs and produces outputs. And so the idea is that you write your program in like Esterel or Luster. I'm being ambivalent between these two because the designers of those two languages actually overlapped. And the tool that they built has two front ends, one which accepts Esterel and one which accepts Luster. And what their compiler did was it took the programs that you wrote, which had like high-level primitives like accepting inputs and signaling outputs, and then it converted that into a finite state machine. And then once you had a finite state machine, it would generate some low-level code. I forget what it did in the 1980s, but these days it generates like some like C code in a big while loop. And all this stuff has been through like a huge amount of certification and assurance effort, and it's used by like a whole bunch of French aerospace companies and like heavy industry companies to do things like to verify the flight control instrumentation of like various fighter planes and passenger jets. And so they know, because they compile from a finite state machine, that there's no memory allocation anywhere. And because they're compiling to a state machine, again, they know that there's only one single while loop. And so assuring that like nothing ever gets stuck is very easy. And so they can implement user interfaces with a high degree of assurance that like, you're never going to get like that little spinning circle that you get on like, your phone or tablet or anything. So this was like a very specific domain, but a very successful one, where people took interaction seriously and then designed languages that had some very good properties. And in fact, this idea of having a state that you can render as output and reacts to inputs is one that's like widely used in even in front end web dev to this day. So like if you program in the Elm programming language, which is a functional language that's used to some extent in front-end web dev, it has what's called the Elm architecture. And the basic idea is you have a state and then like a big loop that receives events, processes them, and then emits like updated HTML documents, which is the new state of the output of the web page. And ideas from Elm were adopted even in like very popular toolkits like the Redux state management for React. And so this turns out, when it's applicable, to work really well. But it's not always applicable. So I want to talk a little bit about the limitations of like, this basic synchronous model. And I'm going to do this by showing you a screenshot of of a code editor many of you may use, so VS Code. And so I took this off the Microsoft website, and this is one particular configuration of VS Code. So on the left, you have like this list of files and places you can jump to. On the right, you have two editor windows showing you two different files that are open, and then down at the bottom, there's like some terminal window where you could click into and type some more commands in that good old 1970s way. And it's okay. So this looks, when you look at it, it's like, okay, fine. I can certainly see how to model interaction with this particular user interface. And then let me show you another window, another configuration that VS Code can have. And in this one, the terminal window is gone, and we have two files that are open, and we have a display of some markdown documentation, and then we have some tabs up here which are files that aren't open. And the thing to notice is that the state in the UI state in these two windows is totally different. It's the same editor, but the UI state is in a very different situation. And this turns out, when you're building things using this synchronous model of interaction, this turns out to be really difficult to account for. And the reason is that we had drawn this picture where we said, okay, we have a set Q, which is the set of possible states that the computer can be in, a current state and a state transition. And the issue is that the set of possible states can vary dynamically. So if you just think about cursor positions, then in this window right here, there's like sort of two sensible cursor positions. There's one for the window on the left, and one cursor position for the window in the middle. But in the previous screen, we have three possible cursor positions. So one for the top right, one for the top middle, and one for the bottom. So there's 3 places your cursor can be versus 2 places here. And so the set of possible cursor positions is changing as you open and close tabs and display more or fewer things. And that means it's actually very hard to just sit down up and enumerate the set of possible states that VS Code could be in ahead of time. And if you think about things like the ability to download plugins for VS Code, like the idea of enumerating every possible state that the editor could be in, like that becomes even more impossible. And so the question is, or one question is, like, what do people do about this? So the Elm architecture, or the synchronous programming model, is great when it applies, but it evidently doesn't always apply conveniently. So what can we do? And so what we can do, the answer to that question, actually, I guess the first successful answer to that question was invented by this fellow right here, Trygve Renskog, who worked on Smalltalk 76 and Smalltalk 80. And he is the inventor of the model view controller pattern of event-based programming. And so his idea was, the whole thing of you create widgets that you can attach listeners to. And so you can write programs these days where you do things like, okay, I'm going to create a panel, which is going to contain my widgets. And then I'm going to create a label widget and a button widget. And I'm going to add an event handler to the button that says, whenever the button is clicked, change the text to something else. And then I'm going to add these two widgets, the label and the button, to the panel, and then that's my program. Okay, so what does this program that Trygve Renskog taught us to implement? Like, what does it do? What does this programming model do? And the answer is that, the first thing it's going to do is it's going to give you a little window. And in this window, there will be a label marked hello, and then there's a button that you can click. And then what happens if you click this button? So you try clicking the button, and then what happens? Well, when the button is clicked, we're going to invoke the event handler. And then that event handler will modify the state of the label to change it from saying hello to saying goodbye. Okay, so now we've taken this old model of, we have a fixed set of states, and we've sort of radically altered it, because now we can dynamically create state that we add to our UI. And so how does that work? Well, it turns out that there is still, this fundamental event loop that's at work. So the way that the UI works is that somewhere in your language's runtime system, there's a big while loop. And what the while loop does is it's going to have a blocking function to get the next event. So that thing right there. And so you're going to wait for the next event to arrive. And let's say that, the event that happens is a click event. Then what you're going to do is you're going to go look up some table which has all the possible events and all the possible handlers that need to be invoked when that event happens. So because we were clicked, we're going to go look up in this big table to see which event handlers to run when a click event happens. And so we look up in the table and we get this list, G1, G2, whatever. And then for each of those functions, we're going to call it. We're going to say for each handler, G1 to Gn, we're going to pass it the event data and have it do whatever it's going to do, whatever state it's going to modify. And the way that these onClick methods work is that whenever you invoke something like button.onClick, what you're going to do is you're going to modify this global table and add the event handler that you wanted to register to this table. In fact, like in an actual GUI, it's even more complicated than this, because instead of having a table, it's actually a tree, and events flow up and down this tree. But that wouldn't fit on the slide, so that's not what goes here. Okay, so we have this event loop, and what the event loop does varies dynamically. So unlike having a state transition function that says when I see this input and my current state, I transition, the state update that we do is mediated by an indirection. So foo is a handler, so it's a piece of code that you store in this table, and then when the event arrives, you dynamically look up which bits of code to run. And so this is like a massive gain in flexibility. But the basic issue in life is that unless you arrange things very well, there are trade-offs, and so event-based programming of the style that we've done for the past 45 years, it has a certain number of problems as well, and the problems can be summarized in sort of 3 bullet points. The first is that it's a concurrent programming model. So you imagine that you have different buttons, and each button in your programming model you assume can be run independently. Like the keystrokes and the button clicks on different widgets, they all happen independently, and because of that independency, there's this logical concurrency in your program. So you have to think about your GUI program as a concurrent system, and as everyone knows, like concurrency, even logical concurrency, is very challenging to get right. And the second problem is that in order to make the system flexible, we have to turn to some very powerful primitives. So one of those things we have to do is we have to program with higher order functions. So if you look at the enumeration of the handlers, we look up some functions in a data structure, and then we call those functions. And we don't know what they are statically, and in fact, they can change dynamically. And okay, so higher order functional programming, I really like it, but it's something that I know just from watching my students that they find very challenging. And then even if concurrency and higher order functions aren't difficult enough, all this stuff is done through some extremely heavily aliased global mutable state. So if you've programmed in like Cocoa or GTK or the JavaScript DOM, you'll notice that there's this thing which people call the scene graph, and everything in your application, and it represents your UI, and everything in your GUI handling code modifies this global data structure, and it modifies it by adding and removing higher order functions, and like verifying these kinds of programs is actually one of my academic specialties, but it's really hard. So if one of my students, took some interesting program that was either concurrent or had lots of higher order functions in it, or had lots of mutable state, and they proved something interesting about it, they would get a PhD. And now what we're saying is that like every single one of these programs, it's like every UI program you write, it's sort of worth 3 PhDs if you like really think about it to get it working right. And somehow we're asking, we know from the point of view of semantics that this is incredibly challenging, and we're asking millions of front-end devs to handle the hardest problems that we know how to express in programming language theory. And so this seems almost unfair, an unfair ask in my opinion. And okay, I'll tell. And as an aside, about a decade ago, Adobe decided to do like an inventory of the software engineering inventory on like Illustrator and Photoshop, like that suite of programs. And they discovered that bugs in UI code, like buttons doing the wrong thing, sliders not changing the appropriate value, those kinds of bugs represented about 2/3 of their bugs. And their UI code represented about 1/3 of their total code base for a program like Photoshop or Illustrator. And when I learned that actually kind of blew me away, because these people are implementing like incredibly intricate image processing algorithms that use like super advanced mathematics, and they're doing like these incredibly optimized implementations in low-level C++, and that stuff is easier to get right than like their save dialog. so that really struck me, and it's one of the reasons I've been interested in UI programming languages. So what can we do about this? Because it almost seems like we have a sort of engineering trade-off, where on the one hand we have like a simple synchronous programming model, which is very mathematically tractable. We know how to generate really efficient code for it. You can analyze it very well and use it in safety critical systems, but it's totally inflexible. Like you figure out all the data that your UI has up front, and that's the end of the story. But on the other hand, we have like, the sort of modern model view controller style of event-based programming. And this is super flexible. You can implement anything you like in it, but it's like punishingly difficult to reason about. So from a semanticist point of view, we have to like break open the toolkit and take every idea in semantics to say anything about these programs. And when programmers actually try to write these programs, they find it difficult to get like, totally correct. Like it's hard to test. And if your tests tell you something is wrong, it's hard to figure out what actually went wrong, because there's so much indirection and so much concurrency in these programs. And so this seems like a sort of unsatisfying state of affairs. There's always a temptation as an engineer when you see this sort of thing to think, there must be a trade-off. But like, as computer science researchers, I think we should resist that urge. Because computer programming is a really new discipline, and there's no reason to believe that we're anywhere close to the Pareto frontier. Like, it seems like I think it really is possible to make things that are just better in all dimensions. Like we're nowhere near the point where we have hard trade-offs. Like by thinking clearly, I think we can make things better along every dimension. And so I'm going to tell you now now that you have this context, I can tell you a little about some of the work that I've been doing in this regard. Okay, and so, but before I get to my work, I want to talk about a line of work that's been very popular in the functional programming community for about 25 years. So in 1997, Conal Elliott and Paul Hudak made an observation. And so what they observed was that if you look at an interaction like this, so you have like a interaction with a terminal where you give it a command and read some output. The way that we're modeling this is via state transitions, and you think of it as ls is an input, and then it gives you back the current same state of the file system, but prints out the current list of directories. And then when you do a RM, it's going to update your file system to remove talk.pdf and give you an updated system state. And they said, okay, well, we have these sequences of transitions, and why don't we have a sort of shift in perspective? And we're not going to think of like this atomic transition as the basic unit of programming. Instead, what we're going to do is we're going to try to model our programs as something that a program is something that takes in an infinite stream of inputs and produces an infinite stream of outputs, or a potentially unbounded stream of outputs. Okay, so what is a stream anyway? So let's say, okay, so we want to forget about the state and just talk about the inputs and the outputs. But what is an unbounded stream? And a stream mathematically is just a stream of A's is just an infinite sequence of A's. So A0, A1, A2, A3, and so on. A computer obviously can't represent an infinite set inside of it. So what we're going to do is we're going to represent a stream as a program. And so a stream is a bit of code that when you ask it, it'll tell you what the first element of the stream is, and then wait for you to ask for the next element of the stream. So it's sort of like an iterator in Java or Python or something. So that's a good example of a stream. So it's an iterator in Python is not a list or anything like that. It's something that a piece of code that when you run it will successively give you elements of this stream. Okay, And once you have streams, what you can do is you can have like an API for manipulating streams. That's hopefully easier to understand than like manipulations of surgery on state machines. And so you can do things like say, okay, my API is going to include the head function, which if you give me a stream, it's going to give you the first element of that stream. And then there's a tail function, which says, okay, if you give me a stream starting at A0, A1, and so on, I'm going to throw away the first element and give you the stream starting from the next element. And you can also map over streams. So maybe if you have a function from A to B's, you can apply that function f to every element of the stream and turn a stream of A's into a stream of B's. And if you think about this as an iterator, all what you're going to do is you're going to say, every time you produce the next element, you apply f to it. And now you have that element of B that you were hoping for. So we're producing unbounded streams of elements, and we can using an API like this, we can write programs that manipulate streams. And so, here's an example of a program that manipulates stream. Here's a function ints, which takes an integer and then gives you a stream of integers that counts up from that number. So if you call ints O with n, it's going to give you n first and then recursively produce the stream ints n plus 1. So if you call ints 0, it's going to give you 0, and then the tail of that stream is going to be ints 1. And then if you unfold it a bit more, you're going to get 1 and then ints 2, and then so on. So as you go on, you're going to eventually enumerate all the integers starting at 0. And you can use previous values of the stream to construct later elements of the stream. And this is important for modeling interaction. So here's a really simple example. So here's an add function. It says, give me a number and a stream, and I'll start adding up the elements of the stream. So if you start with a stream n0, n1, so on, and a current value k, what add is going to do is it's going to say, okay, my next element is going to be n0 plus k, and then I'm going to call add on n0 plus k and n1, and so on. And so let me give an example, because I think it'll be easier to understand from an example rather than me trying to talk through this code. So if we call add 0 on ints of 1, so ints of 1, recall, is going to give you the elements 1, 2, 3, 4, 5. So what we're going to do is we're going to say, okay, the first thing is we're going to return 0 plus 1, and then we'll call add on 1, and then the tail stream 2, 3, 4. And so then we'll add 1 plus 2, and our next element will be 1, 3. And then we'll call add 3 on the stream 3, 4, 5, whatever. And so we're going to enumerate the sequence 1, 3, 6, 10, 15, 21. So we're adding up all the elements of the stream as we go along. And so by writing programs like this, it turns out to be quite nice to write interactive programs. So we write programs which manipulate streams, and we think of the streams as being sort of like iterators that are either giving us the inputs from the outside world, and we're producing iterators, which are the outputs that we're giving to the outside world. And so if you read Conal Elliott and Paul Hudak's 1997 paper, Functional Reactive Animation, like everyone who reads this paper is like absolutely blown away by how elegant it is. Many people who read this paper go off and try to implement this this system by themselves, and everyone succeeds, and they find out that all of the examples in the paper work perfectly, just the way that they're supposed to in the paper. But anything that falls off the happy path even slightly leads to like difficult to debug, totally inscrutable error messages. And so here's an example. I'm going to start with an example of the sorts of problems that you see in FRP. So what we're going to do is we're going to see basic FRP, which you've just seen. It's just programming with streams or iterators. And now we're going to diagnose the problems that simple FRP has, and we're going to fix them one by one. So what's the problem on this slide? So here, what we've got, what I want to do here is I want to write a function trade, which takes in a stream of prices and then emits a stream, say stock prices or something, and emits a stream of buy or sell orders. And so what we're going to do on this first line right here is we're going to take the head of the stream to get the current price. And then what I want to do is I want to find the price tomorrow, and I'm going to sorry, the stream starting from tomorrow, and that's going to be the tail. So we have a stream of prices. So the head of the stream is the price today, and the tail of the stream is going to be the prices starting tomorrow. And then I'm going to write some slightly sketchy code. I'm going to say if today is less than head of tomorrow, then I want to issue a buy order and then resume trading tomorrow. Otherwise, I want to issue a sell order and then resume trading tomorrow. So this is actually a perfectly well-defined mathematical function. But if you tried to run this program, you would be very lucky if your program hung. Because what you're trying to do is you're trying to access tomorrow's price right now. So this thing right here is a violation of how the world actually works. So if you're thinking of streams as infinite sequences, mathematically it's perfectly well defined to say, tell me the current value and tell me the next element in the sequence. And that's perfectly well defined, but it turns out to be something that doesn't make sense when you're thinking about streams as inputs and outputs. You can't get tomorrow's price until tomorrow actually happens. And so what we're trying to do is we're trying to break causality. We're trying to access future information in the present. And so in FRP implementations, if you're lucky, your program will lock up. If you're unlucky, your program will lock up until tomorrow when the head becomes available, and then tomorrow it'll issue the buy order. And so your program will be sort of shifted by one and do exactly the wrong thing. Okay, so how can we fix this problem? And what we're going to do is we're going to turn to temporal logic, but we're going to turn to it in a slightly unusual way. So temporal logic was invented in the 1970s to invent model checkers, and we're going to apply it in a slightly unusual fashion. So what we're going to do is we're going to say, okay, we had this stream API where we had operations like head and tail and cons, and so tail took a stream A0 to A1, A2, and gave me the result stream A1, A2, A3. So it's giving me all the elements sort of shifted forward in time. And so what we're going to do is we're going to change the types of these programs. So what I'm going to do is when I call tail, I'm going to say, I'm going to write bullet here, and I'll tell you how it's pronounced in a second. Instead of taking the tail doesn't give you a stream back, it gives you a bullet stream or a later stream. And what cons will do is it says, okay, if you give me a current value and a stream starting later, I can reassemble that to build a stream. And now what will happen is if you remember this problematic expression here where we tried to take the head of the price tomorrow, what will happen if you try to do the head of the tail of x's is you'll get like a nice red squiggly, and it'll say, okay, head wants a stream. But when you take the tail of something, you're going to get a later stream. So taking this head doesn't work. And so I've been calling this little bullet thing later. And so what do I mean by that? And so if you've hung around programming languages people, you've probably heard of something called the Curry-Howard correspondence. And the Curry-Howard correspondence is that connect sort of primitives in a functional programming language end up having a correspondence in propositional logic. So if you think of the type of pairs A and B in a programming language, that's a pair. You have one A and one B. And when you read it in terms of logic, you think of this as conjunction. You think of this as A and B. Similarly, if you have a plus B, this is sort of an enumeration type like you get in Rust. So it's either an A or a B with a tag telling you which way to go when you do a pattern match. But logically, it corresponds to OR. So it's either an A or a B. Okay, that's good. And function types in programming, A arrow B, correspond to implication in logic. And what we just did on this previous slide is we introduced this bullet type constructor. And so now we can ask the question, what does bullet A mean from a logical point of view? And the answer to that question is that it's the next connective from temporal logic. So we had this delay operator to delay evaluation, and what its logical interpretation is it has a good logical reading. It's a reading from logical interpretation. It means on the next step. So we can read this type bullet A as saying, I have an A, but not today. I'll have an A tomorrow on the next instant. So it's a delayed A. Okay, and that gives us a way of reading what these types are telling us. So over here, this is telling us if you take the tail of a stream, so now we're imagining these streams to be things extended in time, just like inputs and outputs. If you take the tail of a stream, the tail only starts on the next time step. And when you're assembling a stream, you have the head of the stream, which is on the current time, and you have a stream starting at one step in the future. And you can put those together to get a stream starting now and carrying on into the future. Okay, so this was a real breakthrough, and I came up with this in a paper in 2011 with my co-author Nick Benton. And when we figured it out, we thought, okay, we've really nailed the problem of reactive programming. We can solve all kinds of problems now. And then when we actually implemented it, we discovered that our programs were leaking memory like a sieve. And what made it worse was that sometimes the same program would be okay or bad just depending on the type. So we had this constant function. You give it a number and it gives you a stream that's constantly that number. And that was fine. But if you applied constant at the type of streams, then it was disastrous. So, if you have the stream 1, 2, 3, 4, 5, and you just wanted to repeat it over and over again, whenever we implemented it, we would leak tons of memory. And it took a bit of thinking to understand why. So remember that we were thinking of streams sort of like iterators. They're bits of code that you execute, and they enumerate elements of a stream of the stream. So you have a stream ABC that's enumerating the letters of the alphabet, and at time 0 it's going to give you A. At time 1 it's going to give you B. At time 2 it'll give you C, and so on. Time 3 it'll give you D, and so on. And the thing to remember is that what the constant function is doing is it's saying, okay, give me the stream A, B, C, D, E, F, G. I want you to repeat that stream over and over and over again. But the actual stream that you got as an argument, it's this little machine, and it's enumerating the elements one by one. And so after it's enumerated an element, it doesn't remember what its old elements were. And so you have to, if you want to keep producing those elements, you have to remember all the old elements that were originally produced. And so what this means is that at time 5, if you call const on that, const of x's, that has to give you the elements A, B, C, D, E, F, G, but x's has moved on. It's at time 5, its current value is F. It doesn't even know what A, B, C, D, E, and E are, so you have to remember that. And so you have to buffer those old elements. And you can see right here that if you need to remember k elements at time k, then if time is advancing at like 120 frames a second, you're going to be using up a lot of memory really quickly. And so this sort of explained why our programs were running okay for a minute or two and then turning the machine very, very sluggish. And until we started swapping like mad. And the reason was that we had written programs that were buffering like mad. Okay, so now what we did to solve this problem was we turned to temporal logic again. And so we introduced a type G, which was the type of things that were usable at any point in the future without having to do any buffering at all. And so streams are not bufferable, but things like integers and Booleans and strings, they certainly are. And so the type of our const function now said, give me something bufferable, usable at any time, and I can give you an infinite stream of that thing. And so the definition now said, okay, I have X, and then I use it in the future to keep producing X. And so because we're using X at two different times, we needed to restrict const to only work on things that could be used at any time. And then what we discovered is, okay, this type constructor that we introduced, it had a perfectly good logical reading. I've got a question. Or am I running out of time? Okay.
Both. It is 11:30, just so you know.
Okay.
Wrap up as whenever you can.
Okay. Yep. Okay. So the question was, how do you get an A from a future A stream? Okay. Let me pop back here. So here, so the stream starting at B. Actually, I'll start here. So what we've got here is a stream, and its current value is A. And the future stream is a stream starting B, C, D, E, F, G, but it's only going to start producing values on the next step. So over here, we're saying I have a stream that's going to start producing elements tomorrow, and I have an element that I can use right now. And so you can put them together to say, okay, on the current time step, I'm going to give you my first argument. And then starting on the next time step, starting tomorrow, I'm going to start enumerating the elements from the stream that starts working starting tomorrow. Was that clear?
If I can interpret the question a little bit, I think it's maybe like, what is the elimination form of later? Like, how do you actually deconstruct such a value?
Okay. So this is something that I sort of elided a bit in the interest of not showing you lots of typing rules. So let me show you right here. So I said here we're now, and here we're in the future. And the way that the later connective works is that when you're forming a stream, the first element is now, and the remainder has to happen in the future. And so if you have any values which are available in the future, you're only allowed to use them so a later stream only becomes available as a stream on the next time step. So right here, you're allowed to use it as a stream, but on this side, you're only allowed to use it as a later stream. So what you do is you look at the program and you say, okay, each sub-expression, what time is it at? And then the types of your program tell you which variables you're allowed to use when. And then everything sort of works out automatically. Okay, and so, another question? Okay, yep. And so it turned out that these immutable values that you can use at any time, they corresponded to the temporal logic operation of always. And so this was really quite striking. And now I have one last thing, which I will please bear with me, because I can't bear not to talk about the editor for middle-aged computer scientists. I showed VS Code. I have to show like, a proper free software thing as well. And so I have an Emacs here, and it's not doing anything. And like most computer programs, it's not doing anything, because computers run at 4 gigahertz, and I run at like 4 hertz. And so most of the time, my computer is going to be waiting for me. And this next state type that I just told you about how it helped everything so much, it's actually the type of A's that happen at the next available instant. And so it's like sort of the wrong type for expressing waiting until something happens. So if you have a video game where something is happening 60 frames a second, next A is perfect for expressing what happens on the next frame of this program. But if you have like a text editor where the most common operation is waiting, you don't want that. Instead, what you want to do is you want to wait until something happens at some indefinite point in the future. And when we implement it, it turns out to be promises. And when we read it logically, it turns out to be the eventually connective of temporal logic. So temporal logic has been saving us over and over and over again. And there's still some future work about how do we relate these two views of the world, about the things that happen in a retained mode, things happen asleep until something happens, versus the bits where something updates 60 times a second and you don't want to wait. You want to do things straight away. And so relating those two things is hard, but it's something I hope to look at in the future, and I'm very excited about it because there are all these connections to temporal logic. And anyway, like the high level takeaways is that it turns out that interactive programs have like a huge amount of rich mathematical structure. And if you take it seriously, you're led to this view that temporal logic gives you a powerful way of thinking about logic design for language design for interactive programs. And the other thing is that so does looking at the programs people want to write. Because all my work on this was sort of prompted by, I did a little bit of work. I thought I solved the problem. I implemented it, and then I realized that no, actually, there's still more work to be done before we can really say we've nailed the problem of language design for interactive programs. Like we're getting close, I think, but it's been a long road, but it's also very exciting. And so now I'd be very happy to take any questions you have. And I guess I have to wait for 4 minutes.